Hi guys, I'm Farah, and today I'm going to demonstrate how to implement gradient descent for a simple linear regression line. Gradient descent for a simple linear regression line consists of finding a way to maximize or minimize the error and to compute the gradient. So the first step is to pick a random starting point. Second is to take a small step, and then you just repeat this process again, but this time with a new starting point. So following our first step to pick a random point, we have declared it as v, and this basically gets a random number from the range between -10 and 10, and because this is 2, this is only going to have 2 coordinates, but if this number here was 3, you would have 3 coordinates. Now to estimate the gradient, we're going to call our estimate gradient function, which takes an f, which is the function, v, which is the current point, and h, which is the size. This function here returns the partial quotient, which takes f, which is the function v, which are the 2 coordinates, h, which is the size, and I, whether the gradient goes in the vertical or horizontal. Okay, so this line, we add the h to the ith element. So for example, when the element is x, we add h to the x and then we pass the x, or when the element is y, we're going to add h to the y and then we're going to pass the y back. Okay, then we pass in the sum of the squared errors. And sum of the squared errors is it basically calculates the error by squaring it and adding all them up. So the reason you use it is to find an equation that best fits your data set, and also the v and the h. So the sum of the squared error calls the error function. So this basically takes y away from predict y. So for example, if your y is 10 and your predict y is equal to 14, your answer or your error is actually going to be -4. And this calls the not predict y function, which takes the 2 values, adds them together, and multiplies them by x. And this calls the predict y function, which takes in the 2 values, adds them together, multiplies by x. Okay, so to get the new point, we're going to call our step function, which takes in the current position, the gradient, which is the direction, and also the size, which we have here set to 0.01. And this is basically how you get your next v, and here I've just printed it out to check the output. Okay, so for this if statement, we're using the distance function, which is the Euclidean distance algorithm, which is the formula in the square root of x2 minus x1, and you add that to squared, and you add that to y2 minus y1 squared. Now going back to our statement, this basically says if the next point is less than the tolerance, then we're going to calculate the distance. But if that doesn't happen, if that is false, if the distance is actually bigger than the tolerance, then it's going to continue to look. Now if I go back to this and I test out my code using the data set 1, which is these 2 here, these 2, so I just call them D1 and D2. I'm going to pass them in here, and I'm going to print the result. Okay, so here I've got my result. My slope is 1.998 and my intercept is 1.0064. So basically the equation of my line would be, if I round this up, y is equal to 2x plus 1. Okay, so for the next data set, I'm going to take these 2, which is D1 and D3, and I'm just going to change this here. Okay, so the result for this, I get slope is equal to 2.9979 and the intercept is minus 0.99. So the equation of the line would be y equals, if I round this up, 3x minus 1. So next I'm going to be testing D1 and D4. And for this, the slope I get is 5.069 and the intercept is 1.67. So the equation of the line would be y equals 5x plus 2. So the final data test we have to test is these two here. I'm just changing my function to test these two now. And this doesn't quite work because, as you can see, the range between the values is very big. It's going into minuses and then it goes back into positive numbers. So basically our output is bouncing around. So yeah, the same root technique doesn't work with this data set. It's too big, and one way to solve it is that we make this step size into a list with a variety of numbers. Okay, so by doing that, the result I get for the slope is 0.902 and for the intercept is 22.95. So y is equal to 1x plus 23. So this is the end of me showing you how to implement gradient descent for simple linear regression.